In this video, we're going to draw a graph of the cosine function. First, let's review the definition of the cosine function. The cosine function, denoted cos of theta, associates each angle theta with the horizontal coordinate, i.e. the x-coordinate of the point P specified by theta on the circumference of a unit circle. So here at the bottom of the screen, we've got a unit circle drawn. It's got a radius of 1, and angle theta is in standard position. And so based on the definition of the cosine function, the x-coordinate of point P is the cosine value for angle theta. So this distance here that you'd have to travel to get to point P, the x-coordinate is cosine of theta. So the cosine value is the x-coordinate of a point specified by an angle in a unit circle. So now let's go back to our page for drawing the graph. We have a table where we can insert some values for the cosine function, and then we can plot those values on our graph and connect them. First, let's remember the association between angles measured in radians and angles measured in degrees. 2 pi radians is a full revolution, so it's equal to 360 degrees. And half of 2 pi is pi, so half of 360, 180 degrees, must be equal to pi. And half of pi is pi over 2, so half of 180, 90 degrees, must be equal to pi over 2. And 3 times pi over 2 is 3 pi over 2, so 3 pi over 2 must be equal to 3 times 90 degrees, which is 270 degrees. In our table, we have values that increase by 90 degrees, or pi over 2 radians, so what we're doing is hopping around the circle in quarter revolutions. All right, let's go ahead and label our axes. We have 2 pi labeled here on the theta axis, and so we'll take half of that, which is pi, and put it in its appropriate position. Half of pi, pi over 2 we can label. 3 pi over 2 then must fit into this spot. And each tick is increasing by pi over 2. We have 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and we can just continue like this. This will be 5 pi over 2, 6 pi over 2, which reduces as 3 pi, 7 pi over 2, and then 8 pi over 2, which reduces as 4 pi. It's already labeled. And then on the y-axis, we need appropriate output values for the cosine function, since the cosine function is defined on a unit circle, a circle of radius 1, and we're representing coordinates of points on the circumference of this unit circle. The largest value we'll be able to get is 1, and the smallest value is -1. The cosine function is stuck between the values -1 and +1. Its outputs never are larger or smaller than those values because the function is defined on a unit circle. All right, now let's go ahead and rotate around the circle and extract some values for the cosine function. So we'll start with 0 radians, or in degrees, let's just 0 degrees. And that means that we're here in standard position on our unit circle. We haven't rotated at all yet. We're on the positive x-axis. So we specify this point on the right pole, or the east pole, and the coordinates of that point are 1, 0. Cosine value is the x-coordinate of the point specified by this angle, so the cosine of 0 is 1. So on our graph, we can plot the point 0, 1. Now we can rotate pi over 2 radians, 90 degrees. We specify the point on the top of the circle. This point here has coordinates 0, 1. The cosine value is the x-coordinate of a point specified by the angle, in this case pi over 2. And so the cosine of pi over 2 is 0. So we can plot the point pi over 2 comma 0 on our graph. Now we can rotate pi radians, or 180 degrees. Specify the point on the left pole of the circle. And its coordinates are -1 comma 0. The cosine value of this angle pi is the x coordinate, which is -1, so the cosine of pi is -1. And so we can plot the point pi comma -1 on our circle. Can't get rid of that one. All right, there it goes. All right, now we can rotate 3 pi over 2, which is equivalent to 270 degrees, and that specifies the south pole on our circle, this point here, which has coordinates 0 comma -1. The cosine value is the x coordinate, so the cosine of 3 pi over 2 must be 0. So at the theta value 3 pi over 2, we can plot a point at the height of 0. All right. Now we can continue rotating around our circle, rotate a full 2 pi radians, 360 degrees. We specify the same point we started at, the point 1 comma 0. Cosine value is the x coordinate, so the cosine of 2 pi must be 1. So at the theta value 2 pi, we can plot an output at the height of 1 on our graph. And from here on, we can just continue rotating quarter revolutions around the circle. We rotate another quarter revolution after 2 pi to get to 5 pi over 2. We're now specifying the north pole again. The x coordinate is 0. So at 5 pi over 2, we have the cosine value 0 and a dot on the theta axis. Rotate another quarter revolution. We get to the same spot we were when our angle was pi. This angle here, 3 pi, is coterminal with the angle pi. And so we achieve the same cosine value, -1. So we can plot -1 at the theta value 3 pi, rotate another quarter revolution, we get down to the south pole again, the x coordinate is 0, so the cosine of 7 pi over 2 must be 0, and we can plot a height of 0 at the theta value 7 pi over 2. One more quarter revolution, we're back at the starting spot again. Cosine value must be 1 because that's the x coordinate when we rotate 4 pi radians around a circle. So at the theta value 4 pi, we can plot the height of 1. And it turns out that we can't connect these points linearly. We don't get short line segments that form kind of pointy triangular graphs when we rotate around a circle. Instead, we get a kind of curvy wave. Let's clean this up so that we can discuss that. All right. So now when we're at the north and south poles of our circle, when we're rotating around the circle in those regions, notice that the travel around the circle is almost entirely horizontal. We're mostly just traveling along a horizontal line on this little arc of the circle. It's curvy, but it's very horizontal. So we're going to be moving quite quickly in the x coordinate as we rotate around the circle. So in these areas, when our angle is like pi over 2 or 3 pi over 2, we're going to be moving quite quickly. So we should expect the rate of change or the slope of our function to be kind of steep. And compare that with other areas on our circle when we're on the left and right pole. Here our travel around the circle is very vertical, so we'd be moving fast in the vertical direction, but the cosine function only concerns itself with the horizontal travel, and there's very little horizontal travel when we're on the left and right poles of the circle. So when our angle was around 0 or pi or 2 pi, our travel is quite flat. We don't travel very fast horizontally, so our graph of the cosine function will be pretty mellow in these areas. So when we put these pieces together, we get a nice curvy wave. Just like this. I like drawing quarter periods at a time, representing those quarter revolutions around the graph. It allows me to get pretty accurate picture. And this then is the graph of the cosine function.